Hello and welcome. Thank you everyone for listening to my presentation. The topic for my paper is fault detection with the title Signature Investigation of Typical Faults on France's Turbines. My name is Gine Kirkeboen and I am a master's student at the Waterpower Laboratory in Trondheim in Norway. I'm studying energy and environment with specialization within fluid mechanics and hydropower. The next autumn I'm going to write my master's thesis, so this presentation will present the work done in the preliminary work. The focus of my project thesis has been to characterize the normal behavior of a Francis turbine, which means the behavior without symptoms of failure. I will also suggest how to identify selected fault modes with amplitude and frequency analysis. Before I go through the agenda for this presentation, I will present the background. The increased amount of intermittent renewable energy sources entering the electrical grid, together with high price competition on electricity, requires new strategies for the operation of hydropower plants. Due to its high reliability and good regulating capacity, hydropower can provide stability to the grid and flexibility in the energy production. As a consequence, the turbines are forced to operate at off-designed conditions, which affects the dynamic stability of the turbine and can cause undesired hydraulic phenomena. In other words, the turbines are forced to handle tougher operation and prone to more frequent degradation and damages. At the same time, there is an increased focus in the hydropower industry on developing models for fault detection and condition prediction. By implementing real-time monitoring system including such models, a better understanding of degradation may contribute to detect faults at an early stage and reducing potential downtime. I will introduce you to the main parts of my project thesis. First, I will give a brief review of method used for fault detection in the hydropower industry to provide insight into state-of-the-art. Further, relevant theory and method necessary for identify the normal behavior of a turbine will be presented. Steady-state measurements of pressure pulsations are conducted on the Francis model test rig in the Waterpower Laboratory. Peak-to-peak values and frequencies from the measurements are analyzed and related to various hydraulic phenomena, and possible fault detection schemes are suggested. And finally, I will talk a little bit about further work. I will not go into details from the literature review, but present some key findings that has helped form my project work during the autumn. When developing model used for fault detection, sufficient data from both normal and faulty states are essential. Hydropower components are characterized by unique designs, high reliability, and long lifetime, which results in a lack of historical fault data, so learning from faults are not feasible. Finding from the literature shows that this limitation is usually dealt with by building model based on the normal behavior of the system. Normal behavior models aim to learn the typical relations and patterns for the operation of the system without symptoms of failure. In this way, the real measured value from a sensor can be compared with the estimated value from the normal model, and a deviation will indicate an abnormal situation that should be further investigated. Such models can be divided into different categories, often classified as either physical or data-driven models. Physical models depend on the knowledge about the process and the underlying physical phenomena that results in faults. They may be beneficial when detecting specific local faults in the system or at component level, such as detection of different cavitation processes on the runner blade. A study done by Javier Escaler, a researcher from Spain, shows how to detect 4 cavitation processes on a Francis turbine. By first identifying the frequency signatures of each process from vibration and pressure analysis, he demonstrates how the amplitude of each frequency changes when provoking the different cavitation types. The result can be seen from the figure. Data-driven models, on the other hand, aim to find patterns in large datasets to identify unexpected trends and deviations. And due to the complex structure of a hydropower system with interacting components regarding mechanical, hydraulic and electrical equipment, the mapping between the different parameters may be challenging to describe with a physical model. Data-driven approaches allow for discovering non-linear dependencies in extensive dataset based on machine learning algorithms. And these methods are not widespread in the hydropower industry today, but several attempts using artificial neural network and support vector machine have shown successful results. So, when building a normal behavior model, it is necessary to identify the system and the typical failure modes, which is necessary for finding out how these can be detected. Even though hydraulic turbines are reliable, they are subjected to some modes of failure. According to the handbooks of VBL, standards used by Norwegian hydropower companies, the types of failure that occur on the runner blade can mainly be divided into crack propagation and irregular wear. These damages are caused by material defects and fatigue, in addition to cavitation problems and sand erosion. And they are essential a consequence of vibration due to pressure pulsations and hydraulic instabilities in the water flow. These float modes may not directly lead to breakdown. However, it may cause harmful and unstable operation, and if a turbine continues to operate under these conditions, the lifetime will be significantly reduced. Turbines are designed to operate at one operational point called the best efficiency point. The appearance and intensities of the phenomena tend to increase when running outside this desired point. So our first step is to identify the primary sources causing pulsations, pressure pulsations. So, pressure pulsations are flow phenomena that occur inside the turbine and can either be of stochastic or deterministic nature. A common source for deterministic pressure pulsations are the rotor-stator interaction and the part-load vortex rope in the draft tube. The RSI refers to pulsations that occur as a result of the interaction between the rotational runner and the stationary part, as seen from the upper picture on the screen. The frequency of this pulsation will depend on the rotational frequency and the reference system, and seen from the guide vane, the frequency experienced each time the runner blade pass is called the blade passing frequency and can be found by multiplying the number of runner blades with the runner frequency. Yes, and when a turbine operates outside its design point, a swirling component will occur in the draft tube. At part load, the swirling component will move in the same direction as the runner, and the rotating vortex rope can be observed, which you can see to the right on the lower picture. And this rotating rope will induce pulsations in the range of 1/3 of the runner rotating frequency. So, the measurements in this project were conducted on the Francis Model Test Rig, located at the Water Power Laboratory at NTNU. Measurements were done for the open loop configuration at a constant head of about 12 meters. The figure shows an illustration of the open loop circuit. The water is pumped from the lower reservoir in the basement to the upper reservoir in the attic. And from there, the water flows through a high-pressure tank, through the turbine, the draft tube, and the draft tube tank into the lower reservoir again. And during the measurements, the pump turbine runner was installed, which consists of 6 runner blades, and the number of guide vanes are 28, and the spiral casing consists of 10 stay vanes. The pressure pulsations were measured by 3 pressure sensors. One was mounted at the inlet before the spiral casing, and 2 on the upper draft tube cone, 180 degrees from each other, as you can see from the figure. The sampling frequency was set to 5,000 Hz to ensure reconstruction of all frequencies from the analog signal, and the recording time was 120 seconds. Steady-state measurements were carried out for guide vane openings from 4 degrees to 14 degrees at constant rotational speed. The speed was set according to the one obtained at BEP, the best efficiency point, to give a realistic picture of the actual working range for a full-scale turbine. As the system degrades, characteristics of the signal in time and frequency domain may change. MATLAB have been used for analyzing the measured data. Peak-to-peak values are calculated for each guide vane opening with the histogram method containing 97% of the sample signals. The peak-to-peak values give an impression of the intensities of the pulsation, but independent of the frequencies. So, to investigate the origin of these, the signals were decomposed. A spectral analysis of the acquired pressure values was conducted using the Power-Welch method. The method returns the estimated power spectrum by dividing the sampled data into overlapping segments. Each block is then multiplied with a suitable window to remove discontinuity in the signal before the fast Fourier transform is applied. And finally, the resulting periodogram are average over all windows to reduce the variance. The spectral analysis was performed in MATLAB with a hand window and 50% overlap. and 8 windows. So to the result and a discussion of these. The figure to the left shows how the relative peak-to-peak value varies with different guidewire angles for the 3 sensors. The pulsations have highest intensities at low and high loads away from BP. Here the flow entering the draft tube is characterized by irregularities and swirling components, inducing pulsations with high amplitudes. In addition, the peak-to-peak values for the inlet sensor increases from BP towards overload, which can be explained by a smaller volume in the vaneless space, causing more pronounced pulsations with higher amplitudes. When a runner is damaged either through erosion or cracks, this will affect the water downstream the turbine and may increase the intensity of the pulsations in the draft tube. So one way to detect such local degradation can be to monitor the difference between the peak-to-peak values of the inlet and outlet sensors for different operational points. And when the difference reaches a given threshold, an alarm can be raised. These figures show how the inlet and outlet pressure relate to one operating point in normal state. And 94% confidence interval of the pressure signals is illustrated with a red circle on the contour plot. And this figure provides another way to detect local faults, which can be to monitor the pressure relation between the inlet and outlet. Fault modes appearing on the runner blade will change this relation and induce corresponding mismatches, and the red circle on the contour plot may demonstrate an alarm bound of which deviations from normal behavior can be detected. And further, this can be expanded to include more sensors and all operational points, and maybe advanced machine learning algorithm mismatches may be detected more immediately. Frequency analysis was performed to investigate which hydraulic phenomena that occurred for the different operating conditions and which is most dominant. The results from the 3 sensors can be seen in the figures. The frequency plots were analyzed manually, and several of the expected frequencies are identified, where the most prominent ones are the blade passing frequency, seen as 6 times the rotational frequency, and the rain guns frequency, at around 0.27 times the rotational frequency. In addition, several unexpected frequencies appear from the result, and possible sources of these are system frequencies and external influencing elements, which can distort the signal. And the most dominant one appear at a frequency of 0.67 and is observed at overload in the draft tube. And there were no clear source of this frequency, but to further investigate their sources, both this and the other, additional measurements at different rotational speeds would be beneficial in order to divide the rotational speed dependent frequencies from the independent ones. And by continuously monitoring the intensities of occurring frequencies, alarms should be raised if amplitudes increase or new harmonies appear that deviates from the normal characterizations. For example, in case of cracks on parts of the runner blade or detached parts, this will induce vorticities and pulsations in the waterway, rotating with the same frequency as the runner. As a result, the amplitude of the runner frequency may increase. Okay, so to identify the normal behavior of the turbine, the main focus of this project has been to detect different hydraulic phenomena occurring over the operating range. And from the normal classification, alarms should be raised in case of mismatches in sensor relations, changes in the magnitude of expected frequencies, or if new harmonies or unexpected frequencies that deviates from the normal condition arises. But due to a lack of sensors and low accuracy in the conducted measurements, the results from this project should be treated with caution due to considerable uncertainties. The analysis revealed several suspicious observations that have limited the accuracy of a complete normal identification. I will not go through them all here due to the time limitations, but situations that may have affected the results are the varying rotational speed during measurements, a lack of sensors on adequate positions, and an insufficient manual calibration. Thus, careful planning of the number, type, and locations of sensors is crucial. And as the main goal of the preliminary work was to learn how to operate the laboratory rig and how to perform measurements, accuracy was not the main priority. but these experiences have given valuable knowledge for the master thesis. The main focus of this work has been to identify the condition of the turbine without symptoms of failure. And the new variable speed optimized runner designed by PhD Igor Iliev allows for changeable runner blades. So by 3D printing blades, one can simulate various types of faults, such as cracks or erosion. And the master's thesis will investigate how to identify such errors with extended measurements and comparative analysis. In addition, the focus when discussing fault modes have been locally on the runner. This is a narrow scope as other components will naturally affect the unit. Therefore, for further work, it would be interesting to consider the influence of other parts and components as well, such as an asymmetric rotation due to faults in bearings or speed variation due to frequency variation in the grid. Yeah. Okay, thank you so much for the attention.